So it's better? Okay. So today I'm going to talk about this work that I've done with Shota Komatsu, who is also here in the audience. So this is based on this paper that appeared last November, and it's about cross-cap states in integrable theories, generally integrable lattice systems or quantum field theories. Let me start right away by defining what do I mean by a cross-cap state. So we're going to be talking about 2 dimensions. So to define a cross-cap, so we imagine we have like the complex plane. Suppose you have like the complex plane, and you do this identification of a point Z somewhere in the complex plane is identified with a point at the position -1/z bar. So that essentially tells you that if I draw like a circle of a circle of radius 1, then points outside the circle will be identified with points inside the circle. And at the boundary of the circle, points are identified at antipodal locations. So you can forget now of the region inside and work with the fundamental domain outside, okay? You can phrase this operation by just cutting out the disk out of the complex plane and then identify the antipodal points at the boundary of the disk. So if you just cut out a disk, let's now suppose you put a quantum theory on this geometry. If you just cut out a disk, this is usually the way we define a boundary state, right? So we have fields living in this region. So as they approach the boundary of the circle, you have to impose certain boundary conditions, and in this way you define a boundary state. But here, the situation is slightly different. So you impose that this point will be identified with a point there, and this is yet another state, and this is what's called a cross-cap state. Okay, so this is what I summarize here. Cut out the disk from a 2-dimensional surface and identify points at the boundary of disk in this way. And usually we represent this state by a cross. It's really the cross-cap. So now you can do the following. You can put or insert this type of cross-cap states in any geometry. For example, if you start with a sphere and you add a cross-cap, you get another manifold, which is called RP2. It's real projective space in 2 dimensions. You can put 2 of them, 2 cross-caps on the sphere, and that gives rise to the Klein bottle. And these are examples of non-orientable manifolds. Okay. So I already anticipated that this is somewhat analogous to a boundary state. And boundaries and defects are great things to use in quantum field theories or lattice systems in many different contexts. For example, gauge theories, we of course like a lot Wilson and Tufte loops, which are probes for confinement, for example. In lattice systems, putting defects, it's also important, for example, to study one famous example that was important in the study of the RG was the Kondo effect, which is when you have a lattice and you put an impurity. And then there is, of course, in the context of high energy physics, like string theory, where boundaries are nothing else but d-branes, which are certain extended non-perturbative objects that exist in string theory. So how do we study boundary states in general? There are essentially 2 approaches. One is to look at fixed points of the RG flow, at which you have some conformal field theory, and then you use 2-dimensional CFT techniques to determine these states. For example, this is famous works by Ishibashi and Cardi, where they define the general conditions for to have a conformal boundary. And then these conditions are perfectly general. Then you can apply it to specific models. And for example, we now know all the boundary states, for example, for the minimal models. So that's one way of studying, go to CFTs. The other way, perhaps familiar to many of you, is to use integrable models, which are theories that have infinitely many conserved charges. And for those, there is a special class of boundaries for which you preserve an infinite subset of these infinitely many charges. So these are the homologic of Gaussian boundaries or integrable boundaries. And in those cases, integrability is preserved. And so if I have some additional parameter in the theory, I can go away from the fixed point and study completely the RG flow. Okay, but that's very specific for this case of the boundaries. Right, so in the case of cross-caps, already in the original paper of Ishibashi, he not only defined the most generally boundary conformal conditions, but also defined the cross-cap states in the CFT. Okay, and there are many reasons why one should care about cross-cap states. For example, in the case of string theory, which might sound a little exotic, but there are other objects besides the branes, and those are called orientifolds, which are used very much in trying to construct more realistic models out of string theory. There is something recently pointed out, which is that any quantum field theory with time reversal symmetry can be put on a non-orientable manifold, and that gives you insights with regards to the time reversal anomalies, if you want to gauge these time reversal symmetries. There's also some recent interest in terms of the bootstrap. So as I mentioned, cross-cap states are very much similar to boundary states. And usually when you consider a theory with a cross-cap state that breaks partially conformal symmetry, and you can use the remaining, the leftover of the conformal symmetry to mount a bootstrap program, set up a bootstrap program to fix these cross-cap states. And it seems that the structure here is a little bit more rigid than in the case of the boundaries. So this has been studied in conformal field theories, but as far as we could tell, they have never been studied in the context of integrable theories, as far as we could tell. So this is one of those rare occasions where you ask a sufficiently general question and nothing has been done as far as we could tell. So the goal of this talk will be to fill out this gap and say something about cross-cap states in the context of integrable models. So the plan will be very simple. So I will tell you how to compute overlaps between generic states in your quantum field theory or lattice system with a cross-cap state. So this is the kind of things that we are interested in. I will introduce the concept of a P function in integrable field theories. Then I will talk about cross-cap and study the RG flow of this P function. Finally, I will mention something about cross-cap states in spin chains and give you some outlook at the end. Okay, so that's the plan and that was the motivation. I don't know if there's any question so far. Okay, good. Very good. So we are interested in this kind of thing. So you have a quantum field theory. Let's fix. We are now dealing with, well, this is general, not even integrable quantum field theory. So you have some, let's call bulk state, some state in your model, and then you want to consider its overlap with a cross-cap. So how to fix this type of objects? The idea is standard in CFTs or general quantum field theories, and it's convenient to consider a Klein-Bottle partition function into distinct channels. Okay, so this is a Klein-Bottle. So I have a cylinder. At the end of the cylinder, I have a cross-cap. At the end of the other end of the cylinder, I have another cross-cap. Okay, so then I have a circle here of size L, and I have the length of the cylinder of size R. So if I assign time in this direction and space in this direction, this is often called the closed string channel or tree channel, just because I can imagine that I have like a closed string that propagates in this direction. Okay, so let's, and then, okay, as I said, I have a cross-cap state here at the end. Let's compute the partition function in this configuration. So that's very simple. So I have here the partition function for the Klein-Bottle. So it will be sum over closed states quantized on a circle of size L, okay? And then this would be if I didn't have anything else, but now I have crosscap states at the ends of the cylinder, so I have to consider the overlap between this state and the crosscap state. Okay, so this is, if you want, the definition of the partition function in the Klein bottle. Now, suppose I take this R to be very large. Well, then this projects me to the ground state. Okay, so I get to the conclusion that the partition function in the large R limit, okay, gets reduced to essentially the overlap between a crosscap state and the ground state of the model. That clear? Or less? Okay. So this is one channel, but I can do things differently, and I can now assign this direction to be the time and this direction to be the space. So if you pay attention, now I have a state that is defined here and then evolves in that the other direction, this tau direction. But if you really pay attention, the Hilbert space here is defined like this. So you have this state here, or this length here. Because this point is identified with that point, it continues, and then with that point being identified with the other point here at the bottom. So I have a circle, in fact, of size 2r. So I can restrict myself to states that are quantized in this circle of size r, and then it evolves by the time equal to length over 2. So when it evolves by the time equal to length over 2, it gets back to the top with the opposite arrow. In other words, we start with a state which is quantized on a Hilbert space of size 2r, which is this circle here. I evolve by L over 2, time L over 2. If I don't do anything else, I get to a state with orientation like this dashed arrow. So to make it into this red arrow, I have to insert a parity operator that reflects this direction. Okay, so this is the Klein bottle partition function in this other channel. So I can decompose this into, so this is the parity operator that reflects this direction. Sigma goes to minus sigma here. And if I decompose this into parity eigenstates, I get this expression here, okay? Where epsilon is the eigenvalue of the parity operator, which takes the value plus and minus 1. Okay, so here it's a slightly more subtle than the previous case, but still very simple. So the natural statement, the usual statement is to say that these two channels will have to give you the same partition function. So we equate them. So if I take now the large R limit of the previous expression, that has to give me, so this is what I got in the previous slide, the open string channel that I equate to the large volume limit of the closed string channel. So I see that this overlap between the ground state of the theory and the crosscap state is related to the density of states with a weight given by the parity epsilon. Okay, so let's make it a little bit more precise. So let's define a free energy in the usual way by taking logarithm of the partition function. So this, I could call it parity weighted free energy because I sum over states with a weight given by the parity. And so I take the log of the previous expression, and what I find is that so here I'm using this equation. So I take the log of this, I get this piece here, which scales with R, and I get a constant piece. So there is an extensive piece, which scales like the volume of the system. And then there is an order 1 piece, which does not scale like the volume of the system. And then there is subleading corrections. Okay, so if you're familiar with the story of a system with boundaries, this is also what happens in a system with boundaries. In a system with boundaries, you also have something that scales with the volume of the system. And then you have order 1 piece, which has to do with overlap between both states and the boundary states. And this is usually called the G function. Okay, so it's something very well known, very well studied. And this is associated to also the boundary entropy associated to the boundary state. So now we have a different kind of order 1 piece. So we define it, we call it a Crosscap entropy as generalizing the boundary entropy. And instead of having the G function, we call it a P function, just because we had to choose a letter. So the P, actually, no, it's related to parity. So P is the overlap between Crosscap and the ground state of the model. And you define an entropy by taking the logarithm of that quantity. So our interest, so of course, this can be defined for any quantum field theory generically, but now we claim that we can compute this quantity exactly in the case of integrable models. Okay. Any questions so far? Is it more or less clear? Okay. Very good. Let's keep going. So P function in integrable models. So I repeat one equation that I wrote before. So we had this partition function in the so-called open string channel, which is equal to what we determined in the closed string channel. So computing things like that, large volume partition function. So a partition function, when I take the large volume, it's the subject of something very well known in integrable models called thermodynamic Bethe-ansatz. So the thermodynamic Bethe-ansatz is a certain technique that allows you to compute this large volume partition function by saddle point, okay? And it also allows you to compute the order 1 fluctuation around this saddle point. So the one loop determinant around this saddle point. And you know, the thermodynamic Bethe-ansatz gives you the leading piece in the large R limit, which is this ground state energy. But we are interested in this order 1 fluctuation. Okay. So, but this is not quite like a thermal partition function because you have to deal with this parity operator. If it was not for the parity operator, this is literally what we know how to solve using the thermodynamic Bethe-ansatz. But we have to learn how to deal with this parity operator. It turns out that that's actually a very simple problem. Okay, let's do this for the simplest integrable model that we can think of. So let's consider a model that has just one type of massive particle. So the best known example, so this is the Singe-Gordon model, which is the simplest integrable model that exists. Interacting. Okay, for in integrability, when we take a lot of these particles and we take large volume limit, you define the energy eigenstates in terms of a number m of excitations, which are labeled by the momenta. And usually you consider these models in a circle that satisfies some periodicity condition, and that's the Bethe-ansatz. Okay, so that's how we define particles in large volume limit of integrable models. So now this is given by what's called the beta state, okay, which is an energy eigenstate. Okay, under the action of the parity operator, what it does is to reflect the individual momenta. So Pj, which is the moment of the individual particle, goes to minus Pj. Okay, and actually for standard normalization of the beta states, you can show that it's actually 1. So the parity operator acting on a state with a set of momenta, what it does is to reflect individually the moment of each particle. So this tells you immediately one thing. Let's suppose we put like a trace here, these states, okay? So when you compute this trace, you put like a beta state here, a beta state there, in sandwich and sum over. And then you have to compute this element, Pj, like the parity operator in between two states. P acting on that reflects. So this gives you 0 if this set is not equal to minus itself. Okay, so this is a statement that in beta states, they are always orthogonal unless the set of momenta is exactly the same. Okay, so which set of momenta satisfy this condition? Well, or which set of momenta will survive this condition? So it's the states set of momenta like this. So if I reflect P goes to minus P, that goes to itself, or I can include a zero particle momentum. Okay, so this, when I do this sum, only states of this type will survive. Okay, so this trace gets reduced to a sum over these terms under this condition. Okay, and that's equal to the quantity that I want to compute. So this is more like a standard thermal sum, except that you have now this constraint that the set of momenta is invariant under reflection. Okay, so now we can really apply the thermal TBA techniques to compute the saddle point and the fluctuations around it. So probably I don't want to give too many details here, but you basically can split this sum into the only two sets of momenta that survive. Let's call it the first set S and the second set T. So the beta equations are of this type for this set of momenta. For that set of momenta, it's of this type. So you include a zero momentum particle. But then for each individual set, you don't have any constraint anymore on the set of momenta. And this reminds very much like the beta equations that you would write for a system with boundaries, okay? Except that now the reflecting factors now are a little bit different for the S sector and T sector, okay? So you can just recycle the formulae for a boundary case, and you do all this technology, and at the end you get this result. So of course this is a big jump here, but that's the result of computing the fluctuation around the saddle point. Okay, so this is already the order one piece. These determinants are really the result of computing the one loop determinant around the saddle point. So let me just explain briefly this formula here. Just break it into pieces. So the formula is the following. There is this y, which is the y function that satisfies the saddle point equations. So these are the thermodynamic Bethe-Ansides equations, okay, that fixes this y function. So I need to use this y function here, evaluated at argument equal to 0, okay, where these y functions depend only on the S matrix of the model, which is the basic quantity in integrable models. Then I have these determinants, which are actually Fredholm determinants for a kernel, for this very same kernel, which is made out of the S matrix. In sum, to determine this P function, or the overlap between the Crosscap state and the ground state of the model, you just use this formula with the input being the S matrix of the model. So for example, for the Singe-Gordon, it's well known. So you just feed these equations with the S matrix and you get the P function, okay? So this is the result, again, of very standard manipulations in the context of thermodynamic Bethe-Ansides, which it's been known for quite some time, okay? So a little note that we have computed the Crosscap state for this Crosscap overlap for a Crosscap state and a ground state of the model. But we can also generalize for any excited state of that model by something called Dori-Tachio trick or analytic continuation. It's a slightly technical thing, but it's just to say that we can also generalize for any overlap in the model. And an observation is that when we take the asymptotic limit, which means to take L to be very large, then these Fredholm determinants become standard determinants of this type of matrix which resembles very much like these Godin matrices. Okay, so this is it. That's the main result, is that we can compute these overlaps in integrable theories with one single type of particle, but we can generalize. It's also easy to generalize for other types of or the cases where the theories have more different types of particles. So we have to take into account the so-called nested levels when particles carry additional indices. But let's try to see how does this P function behaves under the RG flow. Okay, the motivation to consider this is because in the case of the boundaries, there is a famous theorem, which is the G theorem, that tells you that the G function is monotonically decreasing from the UV to the IR. And it's natural to ask whether this P function could there be something like that. Okay, how do we study that? Well, so this is the goal. So we're going to study this in a particular model, which is a very simple model where we can follow precisely this RG flow. So this is the so-called staircase model that was introduced by Zamolodchikov a long time ago, which is basically the following. So what is this staircase model? So you start with the Singe-Gordon model again. So this is the Lagrangian of the Singe-Gordon, for which the S matrix, the two-body S matrix, is known exactly. Okay, that's the rapidities of two particles. So the two-body S matrix is given by this, where this gamma here is related to the coupling of the theory. Okay, so that's the Singe-Gordon. So notice one thing, which is that this S matrix is invariant under gamma goes to pi minus gamma. So this doesn't change, and this reflects something called weak-strong coupling duality in these models. So there is a duality that maps you the weak couple theory to the strong couple theory. Okay. So the proposal of Zamolodchikov was to say, well, let's look at the self-dual point, which is pi over 2, where this relation doesn't change. Let's do an analytic continuation by some so theta 0 is a real parameter, so this is a complex continuation to the complex plane. So notice that this is something strange to do because this is the coupling, so you are continuing the coupling to the complex value. But the idea of Zamolodchikov is that, okay, so at the level of the Lagrangian, doing this might be a little bit sick, but you get a new S matrix, which is still physical in the sense that it satisfies all the good things that you like. For example, real analytic, it's unitarity, it solves crossing symmetry. So this looks very like a good S matrix. So let's take this model as some some theoretical model that doesn't have or at least the Lagrangian description is not okay, but let's take from the point of view of a model defined by its S matrix. Yeah. That's an excellent question. I think so. And we're gonna see an example of that. You will see now why is it important to do this. So of course, yeah. So you will see what does this have to do with RG? Okay, so let's take this gamma analytically continued. And so what has been noticed by Zamolodchikov is that suppose now you take this theta 0 to be very large. So we are taking complex coupling to a very large value in the complex plane. What he showed is that he computed the ground state energy, which is this effective, also called effective central charge. So this is basically the ground state energy of the model as a function of the volume L. Okay, and now he plotted how does this depend on the value L And you notice that it develops as theta 0 goes to infinity, it develops some plateaus here. And these plateaus are precisely at the values corresponding to the so-called diagonal minimal models. Okay, so the interpretation of this staircase model is the following. So the staircase model is a parametric family of integrable models parameterized by theta 0, whose RG flow as you tune L goes past close to the minimal models. Okay, so these plateaus corresponding to the minimal models, it's well known that there is actually deformation of a minimal model that takes you to another minimal model. So if you start with a minimal model, let's say, for example, here, the plateau of the tree critical, you turn on a relevant operator, and it's known that this tree critical flows to the critical easing model. And so this is the interpretation. So is it clear now? So L, you think of it L as a coupling that as you dial, it flows from various CFTs and interpolates between all these CFTs. Okay. So the idea now is clear, is to, well, let's compute the P function for the staircase model, and let's run L and see how does this thing behave, the P function behave. Right, so yes. Yeah, so but it's not very well known, right? So you know the UV limit of the Sims-Gordon, which is given by the Liouville, but then what happens after that, it's not so much under control. Well, I mean, at least I don't know what happens, but here's an example where you know that you go past CFTs, so you have some benchmark points where you can test. Whereas if you just do the Sims-Gordon and you change the volume. Yeah, right. Because changing the system size is really turning on some relevant operator that interpolates between different fixed points. Okay. So we did that. So we plotted the log of P as a function of L, and we see that it also develops some plateaus, but the important thing is that it decreases so from the UV to the IR. Okay, so these orange lines we can also determine using CFT data. So this is possible to compute. It's just to play the same game as looking at the CFT in the Klein-Borel partition function and look at different channels. So at the fixed points, we can compute these lines, and we see that, as expected, the P function goes past these lines for the minimal models. Okay, so we can compute this. These plateau values are given by these expressions. Okay, so we were kind of happy because, okay, maybe this is general. So then we started to look at other types of models. In particular, the flow that we have seen interpolates between minimal models in the so-called A series, which are like diagonal minimal models. But there's also another thing called D series, which are non-diagonal minimal models, which are obtained by gauging the A series by its Z2 global symmetry. Okay, so essentially the gauging amounts to, so A series contains a Z2 global symmetry, so you identify states up to some Z2. So as usual, when you consider an orbifold, you have to add a twisted sector and restrict the Hilbert space to Z2 invariant states. That's what it means to gauge. At the level of the Bethe ansatz, we can have a counterpart of these things, which is adding a twisted sector is just to consider particles to be antiperiodic. So instead of having 1 in the standard Bethe equations, which are periodic, you put a -1. And then restricting the Hilbert space to Z2 invariant states means to consider even number of particles. Okay, so that's the implementation of gauging at the level of the Bethe equations. So now we can start, take as a starting point these new Bethe ansatz, and we get a new P function for this model that interpolates between the D series minimal models, which contrasts a little bit with what we got before for the A series. Okay, so now we can plot this P function and see what happens. And so it also decays nicely as before, but at the very end, it raises. It increases actually. So the P function is actually not monotonically decreasing. Okay, so it goes to a value which is 1/2 log of 2. Okay, so let's contrast this with the A series. So the A series went to 0. This one increases at the very last step. So the deep infrared to a value which is log of 2. So if you track what it means to go to 1/1/2 of log of 2 versus 0, it means that the partition function in that limit goes in one case to 1 and in the other case goes to 2, which is related to the fact that in the deep IR, this theory has a unique vacuum, whereas here the Z2 symmetry is spontaneously broken. So there is actually some degeneracy on the vacuum, and this explains why you have these two different values. So in summary, strictly speaking, this last step does not belong to the D series in the sense that it's not a diagonal minimal model. So strictly speaking, it ends here at this plateau, which is the 3-state Potts model. Then you have, well, maybe here, this one, this is the tricritical, this is the Ising model, and those are already diagonal. So strictly speaking, if you stop the analysis here, it's still decreasing, but generally, in this case, we face a symmetry breaking phase and then symmetry spontaneously. So we get that the P function increases. So there's, strictly speaking, there's no monotonicity theorem, maybe under some conditions, and maybe these two facts are related, that symmetry breaking and the increase of the P function, maybe there's something here to be studied. But for the moment, it's just an observation in some particular cases. Okay. So, how much time do I have? Okay, that's perfect. Because the last thing I want to say is to talk a bit about cross-cap states in spin chains. So, how do we generalize this story to spin chains? So far, we have been talking about quantum field theories, but we can also have a lattice version of that. So let's take the simplest case, the XXX SU2 spin chain, which is the Heisenberg model. Let's define a cross-cap state by mimicking the definition of a cross-cap in a quantum field theory. So I imagine I have here a spin chain, which is like a closed spin chain. And what I do is to identify antipodal sites on the spin chain. So I entangle a lot this site here with the site at the antipodal location. So that's a site J with a site J plus L over 2. So these two are entangled. So if the spin is up here, it's also up there. If it's down here, it's also down there. And then I define a cross-cap state in this way. Okay. So if you're vaguely familiar with the story of integrable boundary states in spin chains, there is a well-known study that you generally construct integrable boundary states in spin chain by entangling sites which are neighbors, okay, with specific coefficients here. So you have like a spin at the site J is entangled with the spin at the site J plus 1 and so on. So in fact, here the entanglement is short range. So if you compute, for example, boundary, the entanglement entropy in some subregion, you see that it's always very small. Whereas in this case, the entanglement is actually, the state is actually long-range entangled, which means that as you increase the region where you're computing the entanglement, it grows until half of the system size, where it reaches the maximum, and then it decreases. And this dashed line is a generic chaotic state. So strictly speaking, there's really no reflection at this point, because you're just you were referring to the picture that I had with. Right. So strictly speaking, here there is no reflection anymore. The system is closed, because the moment you identify this point with that point, the system is actually closed. But you may be asking, how do I write down the Bethe equations for this system, for example? Yeah. So the previous picture was just an analogy with the boundary state. Yeah. So for the previous case, what I had is like a system of size 2R, which is periodic, but formally it looks like a system of size R with boundaries, but the reflecting factors are just different. But it's just an analogy, so there's really no reflection at this point. Okay, so so what is interesting about this is that one can show that this state, this Crosscap state on the spin chain, is also integrable. And here's the statement of integrability. It's annihilated by infinitely many conserved charges. Okay, and we can also compute the overlap between this Crosscap state and the generic Bethe state, which has this form that we actually have seen before, where these matrices are related to the Godin matrices. Okay, so for example, as analogy with the boundary overlap, you also have, in the boundary case, you have also this ratio, but you have some non-universal factor here that depends on the details of the boundary. So in a sense, you can think of the Crosscap as the simplest possible boundary state formally. Okay, so conclusions. So we studied Crosscap states in integrable models, and the punchline here is that if you have an integrable model and you put it in a background of a Crosscap, integrability is preserved, okay, generally. So that's not the case of the boundary. The case, you have to choose carefully the boundary, but here there's no choice. And with integrability, we can compute these overlaps. We could see that P function is monotonically decreasing for the A series, but not for the D series minimal models. And that might be related to some spontaneous symmetry breaking that you have in the IR. So as outlook, a natural question is there any sort of P theorem under at least certain assumptions? We have seen that these Crosscap states are long-range entangled. So what happens if you start doing quantum quenches using them as initial states, which is something that people have done with the boundary states, which are short-range entanglement, short-range entangled. So maybe this is an interesting question. Of course, we can generalize this overlap formula to more general theories containing, in particular, other types of particles. And this is something that it's more related to our real interest, which is to find a setup in the context of supersymmetric gauge theories that realize these Crosscap states. So thank you very much.
I was a bit confused by your Crosscap. Is the state that you have this pairwise entangled on opposite ends of the circle, are they a solution from the Hamiltonian, or is just a boundary condition that you enforce?
Sorry.
Yeah, this last page.
Yeah.
Yeah, this C state, is it a boundary condition, or is it?
It's more like a boundary condition.
Uh-huh.
It's not it's really not an eigenstate of Hamilton.
But then how is this different from just having a system define a half of the chain and then you enforce an anti-periodic boundary?
Yeah, it's very similar to that. In fact, strictly speaking, this state you can see this as a thermal field level in the infinite temperature limit, where you have like half of the spin chain entangled somewhat with the other half.
So let me just emphasize that this state is defined on the closed chain. This name is L. So it's not a state in the open spin chain. It's a state in a closed spin chain, but we just have depicted some specific state in that closed spin chain. And what is special about this state is that you can compute the overlap between that state and the energy eigenstate, and that has analytic. That's the only thing which is special about this state.
Okay, so it's not like you are solving any eigenstate of the axis X Hamiltonian.
It's not that we are solving eigenstate equations for the open spin chain. It's really like some specific state which is not eigenstate in closed spin chain.
Okay, thank you.
With insight, I mean, it's not at all obvious that you can find some analytic expression for this particular cross-cape overlap. With insight, do you guess some reason why you got such analytic expression?
Well, I think it all boils down to the fact that the Crosscap satisfies this relation, that it's annihilated by infinitely many conserved charges. In the case of, for example, if you start with an integrable model, you can construct all these set of infinitely many conserved charges, and you can find an infinite subset of those that annihilate this Crosscap state.
Okay.
And so I think everything boils down to, I mean, the reason why we can in the end compute overlaps, it's because this condition is satisfied. And in particular, not just computing, but finding, for example, these determinant expressions and things like that.
Okay, okay, yes.
This final expression for the over, it seems that we also get from field.
Yes.
But the spin change works for any system.
Right. Yeah. That's true. They right. But here it's you know, here the moment you do this antipodal identification, you know, it's not that you can take two sides very far apart because of the identification. It comes back to, so this is intrinsically finite volume in the spin chain.
And just another related question, which is this Crosscap state,
The magnetization is not conserved. Yeah. Yeah, that's right. That's right.
Yeah, maybe just continue what Filippo was asking. There were like some other attempts, like for instance, Poshgai Piroli, who also tried to construct from integrable quenches this state. So, do you have any comments why they also obtained analytical answers, or
well,
is
this related to the comment I made here?
Yeah. So just because of half of charges. Okay.
Yeah. So they consider these type of states which were short range entangled, but the observation that this turns out also to be integrable.
Right.
This was, I think, as far as we could tell, people haven't noticed that this could also be integrable. In fact, it's rare to find this type of
I see.
conditions. Like, for example, if you try to entangle this in a slightly different way, it already doesn't work.
I see.
So if you might consider entangle in different positions with different orientations, somewhere, it doesn't work. So the fact that this works was, I don't think people had observed that you could also do that with long range entanglement.